All right, everybody, here we are once again to do some NMR. Woohoo! As you can tell, I am excited. I only can hope that you guys are just as excited as me to learn about the final main feature of interpreting an HNMR spectrum. Once we get this one done, then we can actually start looking at some real-world problems and trying to put everything together to figure them out. Okay, so let's get started. All right, the last thing that we want to go over here is something called spin-spin splitting. And the name here is pretty accurate. All right, so what's going on here in spin-spin splitting? All right, so what I'm going to do is I'm going to take you back to one of the previous videos where I talked about how neighboring protons, each one of the neighboring nuclei within a sample can generate its own magnetic field. And I said previously when we were talking about chemical shift and de-shielding that these nuclei can have an effect on other nuclei. The magnetic field of one nucleus can be felt by another one. So we saw that, they could give you a shielding effect, but they can also do something else. You may have noticed that every one of these spectrums is going to have lines, right? And some of these lines look very, very narrow and straight, and it looks like there's only one of them. And other ones looks like it has a cluster of lines or peaks or curves, right? This is caused by spin-spin splitting. Basically what happens is when a magnetic field of a non-equivalent hydrogen interferes with the signal, then an individual signal or an individual peak can get broken up into multiple peaks within the signal. Okay? So first of all, I want to sort of highlight some of these patterns that we commonly see whenever we have splitting. There's a lot of them that are very regular, right? I'm going to go through several of them. All right? So the first one is called a singlet. I really need a pointier stylus. This is not easy to write with, but that's okay. All right. Singlet is pretty self-explanatory. Just one peak, right? So if you have a singlet, that means you don't have any spin-spin splitting active for that particular group of hydrogens. All right. You add one more peak to it, it can become a doublet. Doublet, as you might expect, is two peaks. And you'll notice here, I drew them about the same size. All right, so if you have a doublet, this doesn't just mean two peaks. It means they're two peaks that are really about the same size, and they appear in a regular little cluster. And that's something that you can look for a lot of these patterns, is that they are true patterns. It's not just, it'll have one peak or two or three or four or whatever, but you see consistent shapes, and also, I'm going to draw an enlarged doublet here. A little bit enlarged anyway. You also have a noticeable gap in between the peaks. This is actually regular from sample to sample as well. A particular signal, a particular type of signal, whether it's an alkene H or whether it's an H next to, an oxygen or something like that, it will exhibit what we call J values. That's a capital J, also known as a coupling constant. All right, and within a given signal, if you have multiple peaks from splitting, they have consistent coupling constants. You're not going to see, for example, three peaks that are going to be like that, where they're kind of wonky and not spaced apart, right? They are going to be nice and regular. All right, and I can use that as a nice segue, to draw the third one. Third one, three peaks. It's called a triplet. And here's what a triplet looks like. All right, and you can see the coupling constants are consistent here between each of these three peaks, at least as consistent as I can draw them with a stylus on an iPad. Right? You'll also notice that they have a pattern of shape as well. They sort of look like a growing mountain, right? Sort of like a mountain, right? You have two peaks on the outside that are kind of small, and then one peak on the inside that is larger, right? So it doesn't just mean 3 peaks. This right here, this is not a triplet. That's because it doesn't have the characteristic shape of a triplet. Okay. Moving along, we can have 4 peaks. Drawing a Q was quite a challenge there, but I did a decent job of it. 4 peaks is called a quartet, and a quartet looks like this. Sorry, I'm trying to draw this on a slanted iPad, so it's kind of leaning a little bit. So you see, very much like the previous one, except it's got 4 peaks. 2 in the middle that are the same height, 2 on the outside that are the same height. All right. Gonna erase. We can have 5 peaks. 5 peaks is called a pentet. Looks like that. You can have 6 peaks. That is called a sextet. Yeah, I messed that one up. Wow, it's kind of wonky looking, but I think you get the point. 2 inner ones the same, 2 middle ones the same, 2 outer ones the same. And then you can also have 7 peaks. That is called a septet. You can see much more, clean versions of these drawn in your book, but this sort of gives you the idea. All right, and then anything beyond septets is just sort of given a blanket name. It's called a multiplet. And we do this because one thing that you're going to notice is that the more peaks that we have, the harder it is to identify all of them, right? For example, in a septet, these little outer peaks right here, I've kind of blown them up here in my drawing, but they get really, really hard to see because they're so tiny. Once you start getting to 8 peaks and above, those individual peaks become so tiny, so small, it's very, very difficult to see them unless you have a really high resolution spectrometer. So a lot of times, anything that's 8 or above is just simply going to be called a multiplet. All right? Okay, so those are some of the patterns that you'll see. Let's talk about the rules that we have to follow to really interpret what's going on whenever you have spin-spin splitting. All right? So I'm going to write a few rules here. All right, so splitting occurs between neighboring sets of non-equivalent hydrogens. So this sort of ties back to that first point we learned about when we tried to figure out the number of signals and being able to recognize non-equivalent proton sets. Splitting only occurs between neighboring non-equivalent H's. All right? If you have H's that are chemically equivalent to each other, they have the exact same magnetic field and they do not split each other. All right, and we said neighboring, that's an important point. When I say neighboring, that means the H's that are splitting each other must be less than or equal to 3 bonds apart. Okay? So for example, let's say we had this guy. Okay, CH3, CH2Br. All right, and it's safe to say that, we should be able to recognize now that we have two groups of hydrogens. Let's say there's group A, there's group B. All right, we're going to see, okay, are these close enough to split each other, yes or no? Well, to do that, just sort of take a representative H from each group. I'm going to put a square or rectangle around that guy and this guy over here. All right, and I'm just simply going to count the number of bonds I have to hop across in order to get there. So 1, 2, 3, they're 3 bonds apart. So yes, signal A and signal B would split each other. Okay? Now if I took this one, all right, this one's going to have 3 groups of hydrogens, right? You're going to have hydrogens here, hydrogens here, and hydrogens here. Okay? So again, if you're trying to figure out which of these groups is splitting each other, just do the same thing. Just grab a representative H from a group and compare it, right? We can see that groups A and B, I think it's pretty safe to say that they're also going to be, just like the previous example, they're going to be 3 bonds apart. So I think it's safe to say that A and B will split each other. The big question is, will signal C be involved in splitting with either of these? Well, let's take a representative H from each group and take a look. So if we start from B, here's a bond here. Whoops. Trying to put a little dot. There's a bond there, a bond there, a bond there, and a bond there. So that's going to be 4 bonds. That does not fall into less than or equal to 3 bonds apart. So signals B and C would not split each other. All right. Signal A is the protons in signal A are even further away, so they're definitely not going to be splitting with C either. So in this case, signal C would be unsplit. And unsplit signals give you singlets. All right, so that's what we mean by neighboring non-equivalent protons. All right, the next thing to remember is that when you're trying to predict how many individual peaks you'll get after splitting, there's a rule you follow. You follow, come on, there we go. Follow the n+1 rule. You get n+1 equaling the number of peaks. So if n+1 equals 4, that means you should have a quartet. If n+1 equals 2, that means you should have a doublet, etc. Now, here's the big thing that people get mixed up on. People get mixed up on what n is. A lot of people think n refers to the number of protons causing a signal. That is not correct. N equals the number of neighboring protons that are causing splitting. The number of protons causing splitting. All right, let me give you an example here. Come on. You know, I kind of laughed at my kid when she suggested cosmic as the color I should use, but actually I really like it. I don't know why. All right, so here's an example. Let's go back to this one. Let's go back to CH3, CH2Br. All right, we have two groups of hydrogens. That one's going to be A. That one's going to be B. So let's predict what we would see for each one of these. All right. Well, if you look at signal A, that protons in signal A, they are split by the two protons in signal B. All right. So for signal A, we would say N equals 2 because there are two protons splitting signal A. So we'd say 2 plus 1 equals 3. And so for that one, you should see a triplet. Signal B, all right, signal B is being split by the three protons of signal A, so N equals 3 plus 1 is 4. That would be a quartet. Okay? And so what I'm going to do now, bear with me while I switch views here. All right, I'm going to take you back to the SDBS. I used this the other day. It's going to tell me I've timed out. So let me just reload it. And I'm going to do a search for this particular compound, the one I just showed you. That is 1-bromoethane. Okay, here it is, under the name ethyl bromide. All right, go away. Come on. There we go. Okay. Old man having trouble with technology. What a surprise. All right, so let's take a look here. Here is the spectrum for bromoethane. All right, and if you look here, I can't, like I said before, I can't circle on this or anything with the stylus. So just look left to right here in the structure. Again, you see signal B is going to be, we're expected to see a triplet, right, because it's split by the two protons of signal A. And we see signal B as a chemical shift 1.679, so it's furthest upfield, and you can see that that is a triplet. Signal A is split into a quartet by signal B. Signal A is at 3.4, and you can see that's a nice quartet there with 4 even lines, right? So it's a good illustration of the N+1 rule in action. All right, let me show you a few other examples here. All right, let's take a look at this one. Come on. I could slow today. Come on. There we go. All right, let's take a look at this one. All right. This is going to be a good example of where to recognize when you have equivalent and non-equivalent protons. All right. In this case, we have protons on this carbon, this carbon, this carbon, and this carbon. Now, this is a symmetrical molecule, right? So hopefully we can realize that the protons here, I'm going to call that group A, are going to be the same as the number of same equivalence as the number of protons here. Likewise, these protons in group B and B are going to be the same as well. All right. When predicting the splitting patterns, if you have symmetry like this, you only have to do it for one side, all right? Because basically, you're going to get a spectrum for the left side, a spectrum from the right side, but since they're exactly the same, they're just going to overlap on top of each other and give you the same image, all right? So in this one, we have 3 H's. If we look at this side, we have 3 H's on signal A. We have 3 of them, we have 2 of them on B, all right? So this one's going to end up very similar to the last one. Signal A is split by the 2 protons on signal B, so that is going to split N plus 1 into a triplet. Come on. There we go. All right, signal B is split by the 3 H's on signal A. 3 plus 1 is 4, so that one's going to be a quartet. Easy peasy. All right, let's try this one. All right, this one looks symmetrical, but it's actually not, at least not the whole molecule, because on the left-hand side of the O we have a tert-butyl group, and then on the right side we have an isopropyl. All right, so let's go ahead first and again identify all the unique groups of hydrogen. All right, I think we can safely say that within this group, these 3 methyl groups all have equivalent hydrogens to each other. All right, so I'm going to say that those are going to be referred to as signal A. Likewise, I think within this group, we can say that the 3 H's on each of these methyl groups are equivalent to each other. They're not equivalent to the ones on the other side, though, so they're going to be their own group, signal B. And also, we have one little H right over there on that carbon. That's definitely different from the other ones. That's going to be signal C. All right, so let's see what we get. All right, signal A, the H's of signal A are pretty far away from the other H's in this molecule, right? They're going to be further away than 3 bonds, so that means they are not going to be split by anything, and they're not going to actively split anything either, so they're not going to be involved. So, when you don't have splitting, that just means that you have a singlet. All right? If we look at signal B, collectively, those 6 protons are split by only one neighboring hydrogen, right? The one on one in group C. All right, so it's split by 1. So 1 plus 1 is 2. That means we're going to get a doublet. And as for signal C, that 1 proton right there actually has the 6 neighboring protons of group B that are actively splitting it. 6 plus 1 is 7, so that one is going to give you a septet. Okay? Not too hard. It's pretty easy. This is all a matter of being able to recognize where you have equivalent and non-equivalent hydrogens and basically seeing how far away they are from each other to see whether they split or not. All right, there's one more rule I want to put in that list that I had earlier, and that is regarding H's that are on heteroatoms. And, if you guys remember, heteroatoms are basically anything that's not carbon or hydrogen. So usually, most of the case, nitrogen or oxygen for our purposes. All right, so H's on heteroatoms are not involved at all in splitting. They don't get split, and they don't split anything else. They basically keep to themselves. All right. Here's a good example of one. This is diethylamine. All right, and in diethylamine, you see we have basically 3 groups of unique hydrogens. It's symmetrical, so these 2 groups are the same, these 2 are the same, and then you have a unique one all to itself on the nitrogen. All right. If you look at signal A, it's pretty easy, right? It's only close enough to the protons of signal B to be split by it, so 2 plus 1 equals 3. It's a triplet. Then you get to the protons of signal B. Those protons are close enough to the protons of signal A to be split, and they're also close enough to the protons of signal C to be split. However, we said the ones on heteroatoms are not involved, so signal B will only be split by signal A. It'll be split into a quartet. All right? And then signal C, we said it's on a heteroatom, not involved in splitting at all, right? So H's on heteroatoms will always give you singlets. And just a heads up, something kind of quirky about these is a lot of times these heteroatom H's will show up as a singlet, but it won't look like a traditional peak. It'll almost look like a little small bump or broad curve or something. All right. Let me show you a spectrum for diethylamine. I couldn't find one on SDBS, so I just Googled one. The chemical shifts are a little wonky because this is actually of a diethylamine salt, but it shows the correct splitting pattern, so I'm going to use it. Over here, you can see, to the upfield side, you have the nice quartet triplet pattern, that we mentioned for the two groups that had carbons involved. And then over here, in this case, at a chemical shift of about 9.5 or so, you see that lone individual singlet of the nitrogen H. And like I mentioned, this one looks a lot different. It's not really so much of a sharp peak, it's more of a little bump. But that's something that you see quite a bit with these heteroatom H's. All right. This is, I always feel I'm kind of got it worked into my robotic memory from doing this all these years that I finish something like that and I have to say, okay, you guys have any questions? Does that make sense? Blah, blah, blah. I have my same things, teachers get into they use their favorite phrases. Mine are, does that make sense? Do you have any questions? It's sort of like slaving and the way it goes, okay, all the time. So if I say, do you have any questions? Do you understand? Please don't think I'm crazy. Alrighty, so unfortunately, splitting's not always that simple. In fact, what you just learned was something called simple splitting. There also exists something called complex splitting. And hey, guess what? It's more complex. Imagine that. Splitting. Come on, give me the G. There we go. Okay, so I'm going to take a similar one to bromoethane, except what I'm going to do is I'm going to add one more carbon-containing group to it. I'm going to make it one bromopropane. All right? So here we've got 3 unique groups of H's. They all see different environments, so they're all unique. All right? So let's try to predict the splitting patterns. Well, if you go through this and see, which ones are close to what, it's pretty easy for signal A, right? You can see it's only going to be able to be split by the protons of signal B. That's going to be 2 plus 1, so signal A gives you a triplet. I'm going to skip to signal C. Again, signal C is only close enough to the protons of signal B, so it's also going to be split into a triplet. Then you get to signal B. This one's a little different because it is close enough to signal A to be split by it, and close enough to signal C to be split by it. And this is where you start getting into some of the more ambiguous elements of reading NMR spectrum sometimes. I'd like to say that it's always going to be nice and neat and clear exactly how many peaks you have, but that's not always the case. All right. So for signal B here, I'm going to go over a couple of different things that you might see. First of all is the theoretical. How many peaks should you theoretically get? And also maybe what may be a little bit more realistic depending on the type of spectrometer you have. Okay? All right. So here's what you do. And I'm going to actually erase some of this so I can get some more room. I'm going to try to leave the formula up there, though. All right. To truly find out the number of peaks you should theoretically see, you have to draw something called a splitting tree. All right? I'm not going to write the name splitting tree up there just because I want to save room, but that's what it's called. All right, so let's say we want to draw what we get for signal B. here's what we do. Draw an individual line. This represents signal B. All right. Then, let's look and see what we would get if this was only split by signal A, and we didn't worry about C. All right. If signal B was only split by signal A, n plus 1 would give us 3 plus 1 equals 4. We would get a quartet. So what you can do is you can draw a quartet coming out of that out of that single line. And that's after you get splitting with A. All right. Then what you do is you do the opposite. You pretend like signal A is not involved, and you draw what you would get if this was only split by signal C. If B was only split by C, you would get a triplet, right? So what you're going to do then is you're going to divide all of these little lines individually into triplets. And I'm going to see if I can actually draw this on the iPad. If I do, it'll be a big accomplishment. Each one of these gets cut into a triplet. So for signal B, theoretically, you would get a 12-peak multiplet. And we can sort of think of this, as being, I'm not going to do a good job of circling these because there's not enough space, but you can see it sort of looks like there's 4 individual triplets over here. So you could call this a quartet of triplets. Quartet of triplets, 12 peaks in total. Question I get a lot of times is, okay, if you have, a situation such as this, which one do we draw first? Like, why didn't I draw the triplet first and then draw the quartets coming from it? So it'd be a triplet of quartets. The rule is that you draw the one first that would give you the widest coupling constant, the J value. All right. For your purposes, you're not going to know that. So honestly, either way you do it is fine. You could have drawn this, as a triplet of quartets, and that would be perfectly fine for your knowledge at this moment. So, 12 peaks. Now, I told you that the more peaks you have, the harder it is to see. And, especially if you have a low-resolution machine. Okay? Such as what we have. The NMR we have, you're not going to see 12 individual peaks. All right, so the 12 peaks is the theoretical, and it might be realistic if you have like a really high-res machine, but here's what we would normally see in our spectra. In this case, the differences between A and C are so minute, according to the machine, it would read them as almost the same, but not quite. All right, so let's do a little hypothetical exercise. Let's just assume what we would get if A and C were equivalent to each other. All right, if A and C were equivalent to each other, then signal B would be split by 5 protons, and it would give you a sextet, right? 6 peaks. However, they're not exactly the same, but they're very close. So what you end up with is something like this. And this is going to be really hard to draw with a stylus, but I'll do my best. Nope, that's not good. Need something with a finer point. Good enough. All right. So you see something that resembles a sextet, but it's kind of jagged, right? You see all these little jaggies at the top? Those are actually individual separations. Each one of these peaks, when you see the little jaggies at the top, that represents the 2 individual peaks that you actually see. So what you might actually see would look more probably like a jagged sextet than a true 12-peak signal. But again, a lot of it depends on how powerful your machine is. All right, let me show you what you would get on SDVS. Whoops, that's the wrong one. There we go. Go away. I just want to return to the home page. Okay, so I'm going to look up that molecule, 1-bromopropane. And my autocorrect wants to call it broom propane. As hilarious as that is, I'm going to say no. All right, and here is 1-bromopropane. All right, and here's the spectrum for it. All right, so, and I'm going to really zone in on this portion right over here. This is our jagged or rough sextet. And so you can, if you look at the base here, you can really see that there are 6 primary groupings, right? But the tops of them are really, really jagged. And if you look closely, you can see some really individual peaks within those. That's going to represent your 12 theoretical peaks. So you can kind of see them, but it still looks more like a sextet, right? And that's really common to the type of thing that you see a lot of times with complex splitting. All right, let me show you another couple of examples here. I know you're probably getting weary. This is one of the longer videos, but we're almost done. All right. Let's try another one. Let's say you had something like this. Random mark, get off the screen. There we go. So it's going to be similar to the one I just did, but I'm going to tweak it a little bit. Put a CL in there. Okay. Again, you know, we definitely have 3 distinct groups here. All right. A, for sure, going to be a triplet. C, for sure, going to be a triplet. Again, we're dealing with what we get in signal B. This time, you know, if we draw our splitting tree, on the left-hand side, it's split by 2 other H's, so that would correspond to being split into a triplet. And then on the right-hand side, also is split by 2 H's, which would correspond to being split into a triplet. So signal B would be 9 peaks theoretically, a triplet of triplets. Okay. However, again, that's not something that you're probably going to see pretty easily on a common NMR. So you might see a little bit more of, instead of a true 9-peak signal, realistically you'd probably see a jagged what? Well, overall it's being split by 4 H's total, so probably a jagged pentet. All right. Hopefully that makes sense. If you have any questions, please let me know. All right, now I want to do one more. I want to show you an alkene, because again, we kind of learned that alkenes are a little bit different. Let's say we have this alkene. All right. Now we learned about alkene H's that they're locked into place. So they, you know, just because they're on the same carbon doesn't mean they're exactly the same. And we can see that these two are definitely going to be different because they're not the same distance away from that Br. And then we have this one over here. So we're going to have A, B, and C. All right. So if you look at A is close enough to B to be split by B, and it's also close enough to C to be split by C. And actually, if you look at all of them, each one of these H's can be split by the other 2 non-equivalent ones. In this case, A, B, and C all give you a doublet of doublets. A is split by, for example, A is split by signal B into a doublet, and those two lines are split into two more doublets by signal C. And the thing about doublet of doublets is that, a doublet of doublets is only 4 peaks, so you can see those pretty well, actually. It will not look like a quartet, right? A quartet looks like this. Whoops. 4 peaks in this pattern. That's not what you see here. This is not a quartet, it's a doublet of doublets. So it's going to look more like that. 2 clusters, both of them, all lines about the same. All right. Okay, so that's going to be the last one I go over now. I realize this has been a long video, but hopefully you guys have gotten a lot out of it. Make sure that you review all of this, all 4 of these, because the next NMR video, we're actually going to be doing some practice problems and putting these together, and shortly I will give you your own assignment to work on. All right, so as always, if you have any questions, just let me know. Until then, I will talk to you later.